Welcome to this lecture series on Maxwell-Boltzmann statistics, where I shall be using my own lecture notes to do one of the most fundamental topics in classical statistical mechanics. And by the end of this video, you will understand how to derive the famous Maxwell-Boltzmann distribution from the very first principles. Maxwell-Boltzmann statistics, often abbreviated as the MB statistics, is the foundation of statistical classical mechanics. It describes the statistical behavior of a system of particles under specific classical assumptions. So let's look at what makes this approach classical. First, it's a classical statistics. That means that it applies to classical systems as opposed to quantum systems. The particles are considered identical in their physical properties, but we can still distinguish them. We can label them as particle A, particle B, and so on, and track them individually. This is the crucial assumption that separates MB statistics from quantum statistics. Unlike quantum statistics like Bose-Einstein or Fermi-Dirac, the intrinsic spin of the particle plays no role in determining the distribution. The particles interact very weakly with one another. Essentially, they are non-interacting. This is similar to the ideal gas assumption. Now let's set up our system. Consider an assembly or an ensemble of n weakly interacting particles. All particles are governed by the same Hamiltonian. The system is isolated, which means the two things. The total number of particles n is constant and the total energy U is constant. This is the microcanonical ensemble. Let the available energy levels be E1, E2, and so on up to En. We assume the particles are distributed such that n particles have energy En, means E1 will have N1 will have E1 energy, E2 will have energy E2 will be there for N2 particles, and so on. In the classical statistics, energy levels are often degenerate. Now what does this mean? Let the energy level EI be the GI fold degenerate. This means that there are GI distinct quantum states, or equivalently GI phase cells in the phase space, all corresponding to the single energy level EI. So the Ni particles with energy EI are distributed among the GI available states. This degeneracy is crucial for counting the number of microstates. We define an important quantity called the occupation probability, or the distribution function, denoted by f of EI. This is the average number of particles per quantum state at a specific energy level. Mathematically, it is simply the ratio f of EI equals Ni divided by GI. This tells us on average how many particles occupy each available state at energy EI. Now we come to the central concept, the thermodynamic probability, denoted by here W, capital W. This is the total number of microstates corresponding to a specific macrostate. The macrostate is defined by the set of occupation numbers N1 to Nn. The calculation of W involves two states. Here, step 1 is the grouping the particles. Since the particles are distinguishable, the number of ways to choose groups of size n1, n2, and so on from a total of capital N particles is given by the multinomial coefficient. W1 equals n factorial divided by the number of all Ni particles. This is the number of ways to partition n distinguishable objects into groups of specific sizes. Step 2 is the distributing of these particles within each energy level. Once the Ni particles are assigned to energy level EI, they must be distributed among the GI available quantum states. Since particles are distinguishable, there is no restriction on the number of particles per state. This is the classical limit. Each of Ni particles can be placed in any of the GI cells independently. The first particle has GI choices, the second has GI choices, and so on. So the number of ways to arrange Ni particles in GI states is GI raised to the power Ni. The total number for all energy levels is W2 equals the product of GI to the power Ni for all the I values. The total thermodynamic probability W is the product of W1 and W2. That's the multiplication of the two steps. W equals n factorial times the product over all of I of GI to the power Ni divided by Ni factorial. This is the fundamental formula for counting microstates in Maxwell-Boltzmann statistics. It tells us how many ways we can arrange n distinguishable particles among energy levels with given degeneracies. The equilibrium state of a statistical system corresponds to the macrostate with the maximum probability. To find this, we need to maximize W. For mathematical convenience, we maximize the natural logarithm of W instead. Since logarithm is a monotonically increasing function, maximizing ln of W is equivalent to maximizing W. Taking the natural logarithm of our expression for W, we get the following equations. We have used the properties of logarithms to separate the products into sums. For very large x, we can use the Stirling's approximation. This approximation is valid when n and for all the ni are large numbers, which is typically the case for all macroscopic systems containing on the order of Avogadro's number of particles. Applying the Stirling's approximation to both ln ni factorial and ln capital N factorial, we get the following expressions. For the most probable state, the variation of ln W must be 0. Since n and gi are constants, we take the differential. Then we follow. This gives us the sum of ln gi minus ln ni minus 1 times the dni equals 0. Carrying on the simplification, this gives us the maximization conditions we need to satisfy, which are the sum of all the particles, that's ni equals n, which implies the sum of dni must be equal to 0. And also this goes for the total energy. We must satisfy this maximization condition subject to the physical constraint of our isolated system. This is a constraint optimization problem, and we solve it using the Lagrange's method of undetermined multipliers. First, the conservation of particles. Second, the conservation of energy. Now we are applying the multipliers. Then we are solving for ni. Let's define a equals e to the power alpha. The distribution function becomes ni equals a times gi times e to the power beta ei. In physics, the constant beta is identified as -1 over kT, where k is the Boltzmann constant and T is the absolute temperature. The negative sign ensures that higher energy states have lower occupation. Using this physical identification, the occupation probability becomes f of ei equals ni over gi equals a times e to the power -ei over kT. Since classical energy levels are effectively continuous, we can drop the subscript I and write the continuous distribution function. And here it is, the Maxwell-Boltzmann distribution function. F of e equals a times e to the power of -e over kT. This elegant equation describes the probability of occupation of an energy state E for a classical system in a thermal equilibrium. The exponential decrease with energy divided by kT is the hallmark of this thermal distribution. The constant A is determined by the normalization conditions, ensuring that the total probability always sums up to 1. That's the end of our lecture and our derivation of Maxwell-Boltzmann distribution. We started from the very basic principles of counting the microstates for distinguishable particles, applied the methods of maximization of entropy, subject to the given constraints, and arrived at one of the most important results in statistical mechanics. Thank you for watching.